Welcome to the Databricks Skill Builder series. We're glad you're here.
Hey everyone, this is Christina Song. I'm a solutions engineer here at Databricks, and today I'm here to give you an introduction to Delta Lake. So by the end of this video, you'll get a high-level overview of the Lakehouse and the Databricks platform, and we'll go into defining what Delta Lake is and how that fits into the picture of the Databricks platform. Then we'll do a deeper dive into the Delta Tables architecture, its features like liquid clustering, and Delta Lake and Uniform. So let's get started. Let me first start off by setting the grounds to help you better understand how Delta Lake and the Lakehouse paradigm came to be. So historically, businesses turned to data warehouses to handle large and growing data sets, and they were mainly built for BI and reporting purposes, and it was meant to unify disparate systems. However, the biggest downside to using data warehouses is that they're expensive, and there's a lack of functionality to handle the modern use cases most companies are looking to solve for, like support for unstructured data like video, audio, or text. And this sort of unstructured data is what businesses are looking to use because it's crucial for modern data science or machine learning use cases. There's also no support for real-time streaming, and data warehousing is great for batch processing, but do not support streaming or can be cost prohibitive. And because they're closed and proprietary systems, they force you to lock your data in so you can't easily move data around. So then this is when the thinking that potentially data lakes could be the answer to all of these challenges. Data lakes and data warehouses actually have conflicting benefits. Data lakes have open formats, so it can store all kinds of data, and the storage is very inexpensive, so it can serve as a great starting point for a lot of enterprises. But the downside to this is that they're missing the data management layer. So there's a lack of structure and organization that leads to them inevitably becoming something like a data swamp. It has very poor BI support, it's complex to set up, and there can be very poor performance. As a solution to these challenges, Databricks introduced the Lakehouse. So the Lakehouse, as you can see from this visualization here, combines the best elements of a data lake and a data warehouse. They use similar data management features as those at work in data warehouses, so it's able to deliver fast query speeds and reliable, manageable data. And they're also built directly on the low cost and flexible storage used for data lakes. So a lake house is able to support for diverse data types and formats, including unstructured and structured data. It has the ability to use BI tools directly on source data, supports diverse workloads like BI, data science, machine learning, and analytics, and it offers data reliability and consistency. So the question you could be asking is, this is a little too good to be true. So what actually makes this possible? It's all thanks to the Delta storage layer. This is really what transforms a data lake to a Delta lake. Delta Lake runs on top of the cloud storage that holds all of your data, whether that's AWS, Azure, or GCP, and it keeps all your data and files in object storage. So this is the central design pattern that defines a data lake. Within the Databricks Data Intelligence Platform, Delta Lake is what sits on top of your open data lake as the foundation for all your other features. This Lakehouse architecture, like I explained earlier, provides you with that flexibility and openness because it consolidates storage, analytics, and ML into a unified system. It also helps you reduce that infrastructure cost, development cost, and maintenance cost. There's no more need for duplicating data for BI and ML. It provides you that centralized governance with Unity Catalog, and this data intelligence platform provides that shared foundation for data engineers and data scientists. On top of that, there's AI tuned to your data and domain. That's a topic for another time, but Yeah, that's the overall Databricks data intelligence platform. So what exactly is Delta Lake? By definition, Delta Lake is an open format that brings performance, interoperability, and ACID transactions to open data lakes. So whether you're using Scala, Python, or SQL, Databricks makes working with Delta Lake super easy. It could be as simple as running a create table statement within the Databricks Data Intelligence platform. Some of the features you'll get by using Delta Lake is listed on the slide over here. It really gives you the tools to reliably store and work with data at scale and includes features like ACID transactions, the ability to time travel to previous versions. You can also enforce or evolve schemas over time. There's also capability for unified batch and streaming, you name it. And the best part about this is that Delta Lake is completely open source and community driven. And looking at the Delta community, Delta has grown a lot since its first launch. There's more than 11 repos in the project. There's been a super fast release velocity with over 50 releases since its launch, and the latest one being Delta 4.0. There's also a very active community behind it, and around half of the contributors are non-Databricks folks, meaning this contribution and diverse community is what's powering the continued development of Delta Lake. And Delta Lake is now used by over 60% of the Fortune 500 and across over 10,000 companies. Delta 4.0 is our biggest Delta release yet, and it's just jam-packed with next-gen capabilities to really help customers meet the growing volumes and variety of data they're trying to access and extract value from. And while I do want to talk about all of these capabilities, for the interest of time, we'll just do a deep dive on a few fundamental and just the most exciting capabilities like liquid clustering. Let's first get started with discussing the fundamentals of Delta Lake, the architecture of it, and the fundamental features. So, within the Delta Lake, you work with Delta tables. And under the hood, Delta tables store data within a folder directory. And within this directory, data is stored as Parquet files. So Delta adds Delta logs stored as JSON files alongside the Parquet files. So Delta table is essentially Parquet files with Delta logs. This transaction log, which is stored in the Delta log directory, records every change made to a Delta table, including actions like updates, deletes, and adds of new data files. This transaction log is what empowers the wide array of functionality to the Delta table. Within the transaction log, we now have access to a concept of table states. So if you insert, delete, or update data in your table, Delta basically adds a transaction and your table stays updated and managed. So with this log, you're able to easily get consistent views of your data and you're actually able to travel back in time. Traditionally, in a data lake, modifying and managing your data could be very difficult. For example, if you wanted to insert, update, or delete records from a data lake file, you would typically need to manually recreate the file with the modifications and keep track of the updates. But with Delta Lake, it's much more performant and a lot easier to use thanks to these transaction logs. Deletion vectors. So before deletion vectors, changing table data required a full file rewrite because Parquet files are immutable. And once they are compressed, they cannot be changed again. So for example, if you have a Delta table with, say, 1 billion rows, and you delete a single record, Delta Lake rewrites the entire table with a new set of Parquet files that excludes the deleted record. Then a new Delta transaction log is created referencing the new files as the current data. As you can see, this process can be very inefficient as it involves rewriting the entire table for just one less row. So with deletion vectors, which is a storage optimization feature that you can enable on Delta Lake tables, with the deletion vector enabled for table, any operations like delete, update, and merge use deletion vectors to mark existing rows as removed or changed without rewriting the Parquet file. So subsequent reads on the table resolve the current table state by applying the deletions indicated by deletion vectors to the most recent table version. Predictive optimization. So this was a feature that was GA'd last year and is specifically referencing as an operation that simplifies management of UC managed tables. For one thing to note is that predictive operation is not supported for external tables and non-UC tables. These tables will still require manual maintenance. But to talk about some of the key features of predictive optimization, first is automatic maintenance. You're able to automate the execution of background maintenance tasks on Delta tables, and this can eliminate the need for manual execution of maintenance commands, which can ensure continuous optimization without any sort of user intervention. There's also it supports maintenance operations like optimize and vacuum. So you can improve query performance by optimizing the file sizes with optimize, and you can use the operation vacuum to reduce storage costs by deleting unused data. So this feature really helps enhance query performance and reduce storage costs, contributing to just overall efficiency within your process. There's also a set and forget approach. Once the predictive optimization is enabled, it intelligently and automatically runs maintenance jobs without requiring any sort of ongoing user supervision. So this simplifies the optimization process, allowing users to focus on other tasks while ensuring tables are continuously optimized. And last but not least, serverless computing. So predictive optimization utilizes serverless compute, meaning it eliminates the need for users to manually manage any sort of compute clusters. And this can help your team, your data engineering or your data team reduce the operational complexity and resource management overhead, providing a very seamless and efficient experience. So what does that mean when you have this enabled in Databricks? We reported that there's been an improvement in query performance by 20 times. It's 20 times faster and 50% reduction in storage costs. So the data intelligence platform really learns how to use your data so that it can optimize your queries and the way your data is laid out. Liquid clustering. This is one of our newer data management techniques that replaces disk partitioning in Z-order. So you no longer have to fine-tune your data layout to achieve optimal query performance. So let's discuss this by looking at an example and how it's done in action. So say you're working with customer sales data. In order to understand why liquid clustering is such a big deal, first we need to understand what's wrong with partitioning today. When you partition this data by customer and date, you find that there are varying number and sizes of files for each partition. There are many small files. This means each small file adds metadata entries, increasing the read-write coordination. It also burdens the file system with excessive tracking. So the query engine needs to scan and handle a greater number of files, and this will in turn increase the input-output operations, slow down data reads and raise CPU and memory usage. There's also a higher chance that there's high cardinality, which can lead to wasted storage. You also find that there are many large size files. This means there's inconsistent file sizes across partition data, reducing the opportunity for distributing workloads across multiple nodes or cores, and limiting system scalability and hindering parallel processing. So in this scenario, we end up with high metadata overhead, slower performance, and inefficiency due to small size files, and data skew and longer queries due to large size files. So this is not what we want, meaning this scenario is probably better suited for Z-order. So when we look into Z-order, Z-order is a file reordering technique that orders files by one or more columns to speed up selective queries via data skipping. So you would use Z-order in the scenario when the query will have to read both files to search for records because the data isn't ordered. Z-order will rewrite the Parquet files within the tables and organize the files by its column statistics. And in this case, the column statistic are the min-max dates. So now that the files have been reordered, the query now only needs to search for the file where the column statistic falls within the defined min and max. So the optimizer knows which files to read and which files to skip. And even with the optimizer, which helps with, which is much better than what you would find with just partitioning, there are still certain challenges where, due to the span of the Z-curve, some files will have min-max range equal to the full range, and data skipping can't skip these files. And Z-order by columns are not persistent, and the user is required to remember the previous Z-order by columns, which, as you can imagine, can cause user errors if different columns are being used. So this is when liquid clustering comes into the picture. Liquid clustering significantly simplifies data layout related decisions and provides the flexibility to redefine any clustering keys without data rewrites. It allows data layout to evolve alongside analytic needs over time, and this is something you could never be able to do with partitioning on Delta. So let's actually see liquid clustering in action. So as you can see in the top right corner of this box over here, the target file size for clustering is actually automatically tuned by Delta Lake based on the size of your table. Or if you choose to do so, you can explicitly set the target file size by using a table property or as an option in the optimization commands. Initially, one file covers several dates for a single customer, and you can also see one file covers several customer for a single date. For a liquid cluster table, newly ingested data is automatically clustered on write for the optimal layout based on the target file size, and periodic optimize command keeps existing data well clustered in the target file size. It also allows you to automatically cluster heavy partitions more finely. So you can subdivide a heavy partition by hours within a day. This is all done automatically, arranging data for optimal query performance without requiring any sort of user intervention. It leverages AI-driven maintenance for continual efficiency and reduced storage costs. So this is all there for you to ensure better performance, reduce costs, and a more efficient use of resources in processing large data sets. Delta Lake and Uniform. So when we're talking about benefits of having a Delta Lake, the biggest benefit is the openness of the platform. So you get very open and flexible access to your data. And part of that is uniform. So prior to Uniform, you had to choose between these table storage formats that largely serve the same purpose. Each of them have different protocols and features, and each of them have different connector ecosystems, which is why different enterprises decide to choose a data lake format. But with Delta Uniform, customers don't have to choose between table storage formats. Customers can write Delta and access as Iceberg or Hudi downstream. So some benefits that come from this from having to not choose the table format, you get just one copy of the data. The Parquet files remain the same, so there's no duplication of data. The metadata is also co-located with the data, so it's enabled for all formats, and it's accessible to any engine in your own storage bucket. And the metadata is also automatically generated for Iceberg or Hudi alongside Delta Lake. And with this unification, you can access the combined ecosystem. The key behind Uniform is that the metadata for Delta can be easily and cheaply converted to Iceberg metadata. At first, if you look at the two metadata formats, they may seem very different. For example, in Delta, as we see each commit file, it's incremental. It's a delta from the previous update. In Iceberg, each commits are self-contained. So it includes all the relevant information about the table at that given point in time. But if we actually look more closely, it turns out that the metadata for Delta Lake and Iceberg are very similar. If you look at the add file action in Delta and compare with the equivalent action in data file, you'll see that they contain the same exact information. It includes the path of the updated file, the partition information, the size of the file, data skipping stats, and more. So Uniform uses this principle to very quickly and cheaply take Delta metadata and generate the corresponding Iceberg metadata. And not only are the metadata formats similar between Delta and Iceberg, the overall flow is very similar as well. So for both formats, writes result in commits which write both metadata and data. The writes can push metadata to a catalog, and to read the table, readers can go to the catalog in order to get the latest metadata, which then points to the data. And so with Uniform, you can simply combine those steps into a single flow, avoiding the mostly duplicated work. So a write to Delta Lake generates commits and metadata for both Iceberg and Delta, and then we push the information to the catalog, which then both Delta and Iceberg readers can query. And in particular, in Databricks, Unity Catalog exposes the Iceberg REST Catalog API, which many Iceberg readers can access in order to seamlessly read the Iceberg. So I just went on explaining a bunch of features and benefits of Delta Lake. I want to bring this back home by discussing one of Databricks customers that found Delta Lake super helpful. So Columbia Sportswear. I'm sure you all are familiar. If not, you might have gotten like a rain jacket from them before. Columbia Sportswear, like most companies, wanted to use their data across their lines of business like sales, purchasing, supply chain, and product optimization. You name it. They probably wanted to use data across all their lines of business. But they saw that their legacy system was taking weeks to ETL data. So as you can imagine, this was an extremely strong headwind towards them becoming a data and AI company because this hinders them from quickly extracting value from data. So with Databricks and Delta Lake, Columbia Sportswear, they were able to build a super high performance ETL pipeline where they saw that the Delta's ACID capabilities significantly simplify their operations. And they also saw that it was significantly more performant access to their data. The outcome was a 70% reduction in ETL pipeline creation time, which is a huge decrease, and a 48 times improvement in the time to process ETL workloads from what originally took 4 hours to 5 minutes. That's huge. So this impact, based on the testimonial from the senior enterprise data manager at Columbia Sportswear, was felt across the organization, empowering business units to self-serve data in a way they never could before. So I want to leave you with that. Let us know if you have any other questions regarding Delta Lake, and if you want to do a deeper dive into the different features of Delta Lake, which we weren't able to go over today. Feel free to check out the links in the description box below. Thank you.